Again, welcome to College Algebra. In this section, we're going to discuss about complex numbers. Again, this is our Unit 7, Lecture Part 3, and we're going to talk about complex numbers. So our main objective is to simplify imaginary numbers. And we know a complex number consists of two parts, the real number part and also the imaginary part. So here we're going to discuss about how to simplify the imaginary numbers, also how to perform operations on complex numbers. When we talk about operations, we mean the arithmetic operation and multiplication, division, etc. Also how to find the powers of I, and also how to determine the absolute value of a complex number. Also how to factor the sum of two squares, which have two complex values. So it's more or less multiplication. So we start with the simplified imaginary numbers. And here we say, for example, imaginary numbers can be a square root of any negative value. If we remember the real numbers, we say always a square root value cannot be negative. So square root of 0 is 0, square root of 1 is okay, but square root of negative 1, negative 10, no, that's imaginary number. It's not a real number. So square root of any negative value is an imaginary numbers. So here we say the imaginary numbers are based on the imaginary unit I, where I square equal to negative 1. So I square, which is the imaginary unit I square always equal to negative 1. Or we say I equal to square root of negative 1. So that's one of the main rules of simplifying imaginary numbers. So if A and B are both negative, then we can say that square root of AB is equal to square root of A times square root of B. It's not the same. So if I have let's say a negative value, A, and B also is a negative value, the square root of A times B is not the same as square root of A times square root of B. So example is given here. We have a square root of negative 16 times square root of negative 4. So we know that square root of negative 1 is I. So here we can say, okay, we know 4 square will give me 16. So I'll get 4i. Why I? Because square root of negative 1 is I. So we get 4i, and our square root of 4 is 2. But again, we have negative 4. So square root of negative 1 is I. And that will give me 4. Now, when I multiply 4 times 2, I'll get 8. When I multiply I times I, I'll get I square. And we know the rules saying that I square is always negative 1. So this means I'll get 8 times negative 1, which will give me negative 8. Now, if I'm having a square root of 16 times 4, the answer will not be negative 8. The answer will be different. So that's the rule here. Square root of AB is not the same as square root of A times square root of B. So square root of 16 and times 4 value together will not be the same. So we know 16 times 4 will give me 64. So square root of negative 16 times negative 4 will give me what? It will give me positive value. So I'll get square root of 64. And the square root of 64 will give me positive 8. So that's what we mean by this rule again. If A and B are negative value, then the square root of AB is not the same as square root of A times square root of B. Square root of 16, negative 16 times square root of negative 4 will give me negative 8. But square root of 16 times 4 will give me positive 8. So we're going to perform some operations on complex numbers. So here we say a complex number is a number that have written in the form of A plus BI. So A will be the real part and BI will be the imaginary part. And that's what we mean here. A is called the real part and B is called the imaginary part. So, okay, a complex number consists of two parts, the real part and also the imaginary part. So, example is A plus BI. A is a real part, BI will be the imaginary part. We know I is what? Square root of -1. So, two complex numbers are equal, again, if their real parts are the same and also the imaginary parts are the same. So here we say if A plus BI and C plus DI are two complex numbers, then A plus BI equal to C plus DI if only A is the same as C and B is the same as D. And this is the rule for equality of complex numbers. Two complex numbers can be the same only if their real part and also their imaginary part are the same. So here, two complex numbers such as A plus BI and C plus D are added and subtracted as if they were binomials. So what we do is that we have a complex number, we have the real part and we have the imaginary part. So if I'm going to combine, or I'm going to add or subtract, I will add the real part together and I will subtract the imaginary part together. Or if I'm doing addition for both, I will add the real part together, I will add the imaginary part together. Or if I'm doing subtraction of both, that here we have A plus BI minus C plus DI, then I'll subtract A minus C, then BI minus DI. So let's see an example. Hopefully the example will help us soon. So if I'm doing multiplication of complex number, it's the same as adding or multiply binomials. Just multiply each term by itself. So A times C, A times B, DI, BI times C, BI times DI. So we have A times C, then A times D, then B times D, then B times A. And again, we will see an example. So hopefully the example will help us. So this is a good example here. We have two complex values and they are multiplied. So -2 plus square root of -16 and 4 minus square root of -9. So what we're going to do, if you like, we will change each number to A plus BI form. And that's what we did here. So we have -2 plus square root of -16, which will give me -2 plus square root of 16 times square root of -1. Because -16 is same as writing +16 times -1. The goal is to get the I. So we get -2 plus square root of 16 will give me 4. Square root of -1 will give me I. So I get -2 plus 4I. The next one we have 4 minus square root of -9. So this is the same as writing 4 minus positive square root of 9 or +9 square root times -1, because square root of -9 is the same as square root of +9 times square root of -1. So we get 4 minus square root of +9 is 3, square root of -1 is I. Now we can multiply the two together now. So we get -2 plus 4I times 4 minus 3I. We multiply all the terms. So -2 times 4 will give me -8. -2 times -3I will give me +6I. +4I times +4 will give me +16I. And +4I times -3I will give me -12I squared. So multiply two complex numbers is like multiply binomial together. You have to multiply all the terms. Now we combine the like terms. So we have 6I and 16I. So we can combine these two and that will give us 22I. 6 plus 16, 22. Then that's it. So we have -8. Now we know that I squared is the same as -1. So -12 times -1 will give me +12. So we get -8 plus 12 plus 22i. Then we combine the like terms, negative 8 plus 12 will give me 4 plus 22i. So that will be our final solution. Again, let's go through this example one more time. So this is the question. They say we should multiply negative 2 plus square root of negative 16 with 4 minus square root of negative 9. Now, because we know a square root of a negative value is not a real number, it's an imaginary, we know that this is a complex number. Now, if I like, we can use the negative 16 times negative 9, but here we are going to deal with a very big values. So the best thing we should do first, let's find the answer for negative square root of negative 16 and also square root of negative 1. So we can reduce the term. So I know square root of negative 16, as we said earlier in the previous section, simplify imaginary part. We know square root of negative 1 is I. So negative 16 is the same as saying negative 16 times negative 1. So I'll get square root of positive 16 times square root of negative 1. That is the same as square root of negative 16. And that's what we did here. And we know square root of positive 16 will give me 4. Square root of negative 1 will give me I. So that's why we get negative 2 plus 4i. The real part, we don't touch it. So negative 2 is still there. 4 is still there. But I know square root of negative 9 is same as writing square root of positive 9 times square root of negative 1. So square root of positive 9 will give me 3. Square root of negative 1 will give me I. So I get 3i. Now, the reason why we convert it to this compressed form is to make the value small lower and the operation will be more simple. We don't need a calculator or any large values. So now I'm going to multiply negative 2 plus 4i and 4 minus 3i. And that's what we have here. Multiply each term by each other, all the terms. So negative 2 times 4 is negative 8. Negative 2 times negative 3i will give me positive 6i. Positive 4i times negative 3i will give me negative 12i squared. And the last section 4i and 4 will give me positive 16i. Combine the like terms, 6i plus 16i will give me 22i. I squared is the same as negative 1. So negative 1 times negative 12 will give me positive value now, positive 12. Combine the like terms here, negative 8 plus 12 will give me 4 plus 22i. And that will be our final solution. So we have something called a complex conjugate. A complex conjugate will take us to something like a difference of 2 squared again. We covered the difference of 2 squared before. So a conjugate means if I have the real numbers, you can say they are the same. The imaginary part also, they are the same. The difference is that the imaginary, one part is negative, the other is positive. So we say complex numbers A plus BI and A minus BI are complex conjugate of each other because they are real and imaginary part are the same, but one imaginary part is positive, the other imaginary part is negative. So example is 2 plus 5i and 2 minus 5i are complex conjugates. So sometimes we may have a question, and the question may say that, find the conjugate of 2 plus 5i. Yeah, the answer will be 2 minus 5i. And then find the powers of I. Here we have some few, excuse me. So we know the powers of I with natural numbers exponent produce an interesting pattern here. So let's see the powers of I. If the power of I is 1, we know 1 of anything is the same 1. But look what happened here. Square root of negative 1 is I. If it's square, the reason why we write this is that I is always equal to square root of negative 1. So if you square 1, something by 1 exponent is the same thing. So we get the same I. But now, when we square root of negative 1, we are looking for I square. So I is square root of -1. So square root of -1 square will give me -1. Now, if it's I cube, it's the same as saying I squared times I. We know I squared is what? -1. We know I is what? I. So -1 times I will give me -I. Then we go to the I to the power 4, which will be square square. So we get -1 times -1, which will give us 1. Then to 5, it will be I4 and 1, which is 1. So you can see how the pattern is working here. We start with I, the next is -1, next is -I, then we start with 1 again, and 1. Then all over again, I, -1, -I, 1. 9 will give us I, then the 10 will give us -1, 11 will give us -I, then 12 will give us 1. So that's the pattern we're trying to say here. So that's what you said. The pattern continues I, -1, -I, 1. So again, 1 square is the same. I mean, I to the power 1 is the same. I to the power 1 is the same I. So we get the same I. But I square will give us square root of -1 is I. So square root of -1, all square will give me -1. Because square will cancel the square root, so -1 left. Then I cube will be I squared times I. We know I is I. I squared is -1. So -1 times I will give me -1. Then I to the power 4 will be I square. So -1 times -1 will give me positive. I to the 5th power will be I to the 4th power times I. And I to the 4th power is 1. 1 times I is I. And we keep going. So let's simplify powers of I. So a question is given here, I to the power 365. So the solution here, we said, we know I to the power 4 is 1. And each occurrence of I4 is a factor of 1. So I to the power 365, I can write I to the power 491 times I, because, excuse me, 4 times 91 will give me 364, so we need 1 more. So times I to the power 1. We know the pattern already. I to the power 4 will give me 1. So 1 to the power 91 will still give me 1. And 1 times I to the power 1 will give me the same I. So the answer will be I. Again, look at the values first. We know in the pattern, previous pattern, we went all the way to 8. But 8, 9, 10 will repeat the same 1, 2, 3, 4. So if I have a 365 value, I don't want to start with 3. I'll start with the largest value, which is 4. So I start with 4. So I say, okay, 4 times what number will give me 365? The closest number is 91. Because 4 times 91, 4 times 91 will give me 364. So I need 1 more, so I to the power 1. And we know I to the power 4 is 1, so 1 to the power 91 will give me 1. I to the power 1 will give me I, so 1 times I will give me I. So again, here we have a power of I. We say that if n is a natural number that has a remainder of r, when divided by 4, then I to the power n is equal to I to the power r. And this is the example we used previously. Now, when n is divisible by 4, the remainder r is 0, and then r to the power 0 equal to 1. This is the rule we use here. So if I have 365, if 365 is the same, let's say if I'm using 364, I know I to the power 364. 364 is divisible by 4. So I will get what? I to the power 491. Because 91 times 4 is 364. So then that's it. My answer will just be 1. But I have 365. The highest I can go, since 365 is not divisible by 4, or 4 is not divisible by 365, Then I need to find the remainder value. The remainder was 1, so that's why I have I to the power 1. Now, if it's 366, then it will be I square will be the remainder. The remainder is 2, so I to the power 2. And that's the rule we use, this rule we use. Next, determine the absolute value of a complex number. So here we have a plus bi is equal to square root of a squared plus b squared. So we say again, if a plus bi is a complex number, then the absolute value of a plus bi will be square root of a squared plus b squared. And that's the only rule we use here. Absolute value of a complex number always is something like a Pythagoras theorem. The imaginary part square plus the real part square or square root. So let's see an example. We have 3 plus 4i absolute. So find the absolute value for 3 plus 4i. This is very straightforward. We know the rule, so it will be 3 square plus 4 square or square root. So that's what we have here, square root of 3 square plus 4 square. And that gives me 9 plus 16. And that gives me square root of 25, and the answer will be 5. But here we have to be careful. Remember the rule said a plus bi is equal to square root of a squared plus b squared. But we have negative 6i. So we have to change negative 6i to positive. So we can see that here we get 4 square plus negative 6 square. And it will be the same, but kind of is good to explain because we need plus. So this will give me 36, 1652. We get 2 square root of 13. Next section, how to factor the sum of 2 squares. So again, we have seen that the sum of 2 squares cannot be factored over the set of integers. But however, it is possible to factor the sum of 2 squares over the set of complex numbers. So for example, we have 9x squared plus 16y squared. Yeah, this is straightforward. We can say 9x squared will give us 3x all square. But here we write 9x squared minus y 16y squared. So minus 1 again is I squared. So we get 9x squared minus I squared 16y squared. Then we get 9x squared minus 16y squared I squared. What we're trying to do is getting the difference of 2 squares. So this will give me 3x all square, 4yi all square. So the answer will be 3x plus 4yi, 3x minus 4y. Factor the difference of 2 squares. So this is the process we follow. And I'm going to, but again, before I end here, let's see this example one more time. So the question here is saying that we should factor the sum of 2 squares. The question is given here. We know we can't do this. We cannot do this in our real numbers alone. What makes this possible is that we know that I square is negative. So this positive automatically will change to negative if I bring in I square. But we have seen that the sum of 2 squares cannot factor over a set of integers, no. Only the difference of 2 squares, we know. But here the sum of 2 squares is possible for imaginary complex numbers. So you can see that the answer we get, even the question was 2 real numbers, but this answer will give us imaginary part now because I make it imaginary part. So again, see if we can square this. We can square this, but this is positive. So let's bring I square and get negative 1. So I square is negative 1. Then we solve it. Again, wish everybody the best. If you have a question about the class and these lectures, again, you can give me a comment down and I'll surely answer your comment.